once again and welcome back to BT35 for the design of reinforced concrete element. Today we are moving ahead to look at our Unit 5, which deals with the design of a reinforced pad foundation. Now, for us to do that, just as we did for our previous lectures, we always set ourselves a question. So this is our question for our pad design. Our question says to design and detail the pad foundation for the column at the intersections of grid lines 7 and C using the limit state method as outlined in the BS 8110 part 1. Now, for the procedure of our pad design, we'll begin by establishing our preliminary sizing. Then we'll move ahead and estimate for the load that the pad is supposed to resist and transfer to the soil. We'll move ahead and do our moment analysis, from which we'll check whether our section that we are designing for or the initial dimensions we came out with is adequate to resist all the moments that the section is supposed to carry. Then we'll design for our moment reinforcement. We'll design for our vertical shear. We'll do our punching shear design, and we'll end everything with our crack design. We are going to make use of an exposure condition which is moderate. Our minimum grade of concrete is going to be concrete grade C35. Our nominal cover to reinforcement for durability in this case will be 40 millimeters. Our minimum dimension being equals to 125 millimeters. The grade of reinforcement, we are making use of a mild steel with a yield strength of 250 newtons per millimeter squared, and the diameter of our reinforcement being equals to 16 millimeters. The bearing capacity for the soil for which we are putting our structure in is equals to 200 kilonewtons per meter squared. So with this basic data being set, we can now move ahead and start with our design. Now we'll start by locating the column for which or for whose pad we are going to design. And the question states that we should design the pad foundation for the column located at the intersection of our grade line C and our grade line 7. And that column has been highlighted with the red mark. Now bringing it back to our structural grid, we'll again come and locate the column on our structural grid. And again, we see it at the column at the intersection for our grade line C and our grade line 7. Now for our initial dimension, we'll begin our initial dimension by first looking at the amount of load that the element would have to carry. And based on the amount of load that the element would have to carry and how much load the soil on which the element is being rested can support, would come out with an appreciable area such that whatever load that the pad is supposed to transfer into the soil doesn't exceed the bearing capacity of that soil. So in order to do that, we look at the total load or the total dead load as coming from the column onto the pad foundation, and the total live load also coming from the column onto the pad foundation. Now, having estimated for the total dead load from the column and the total live load that the column would have to transmit onto the pad, would have to also estimate for the self-weight of the pad itself. As at this point, we don't know how big or how small our pad is going to be. So it will be difficult to determine the exact value of our pad load or of the weight of our pad. So then we would have to assume a value for the pad. Then based on our assumed value, we would come out with a dimension for the pad. Now, to do that, we are assuming that our pad would have a dead load or would have a weight of 30 kilonewtons. Now, to do that, we are assuming that our pad would have a self-weight of 30 kilonewtons. Now, with that one being said, it means that the total weight or the total load that the pad would have to transfer into the soil would be equals to the 150 for the dead load, the 50 for the live load, and the 30 for the weight of the pad itself, which would give us a total weight of 230 kilonewtons. Now, from our design data, we're told that the bearing capacity of our soil is 200 kilonewtons per meter squared, meaning that if we pick per meter squared of our soil space, it can take as much as 200 kilonewtons. From basic physics, we know that our bearing capacity is equal to the load the load divided by the area over which the load is being applied. Now, making the area the subject of our equation will now yield us a formula of area being equal to our load divided by our bearing capacity. Now, with this formula, we can now determine for the equivalent area that we can use to or we can give to our pad such that the load which is being transferred onto the soil doesn't exceed the maximum bearing capacity of our soil. If we consider our service load, we had our service load being equals to 230 and our bearing capacity being equals to 200, meaning that for our service load not to exceed 200 millimeters, meaning that for our bearing load not to exceed the 200 kilonewtons per millimeter squared, the minimum area that we can give to our pad foundation is equals to 1.5 millimeters squared. Now, if we have an area of 1.5 millimeters squared, then what would be the planned dimension of our pad foundation? Assuming that we are making use of a square pad foundation, then it means that we would have to pick the 1.5 millimeters squared and calculate for the square root of the 1.5. That would give us the dimensions of our pad foundation. Now, finding the square root of 1.15 gives us a value of 1.07, which can be approximated to 1.10. So then the minimum dimension that we might or we can give to our pad foundation, such that the load that is carrying wouldn't pierce through the soil that is supporting it, should be 1.10 meters squared. So then ultimately we are adapting a pad dimension of 1.2 meters by 1.2 meters, which is a little bit beyond the 1.1 minimum that we have calculated for. Now, moving forward, we are going to make use of the total thickness of our pad foundation is going to be 200 millimeters. So then by this, we would have come out with the dimensions of our pad foundation. Now, having come out with the dimensions of our pad foundation, we can now move ahead and calculate for the actual weight of our pad foundation. And that would be given to us by the density multiplied by the volume and the acceleration due to gravity. From our previous lectures, we realized that the density of concrete making use of natural aggregate was given as 2307. So then we pick that density value, then we multiply it by the volume of our pad foundation, which is equals to 1.2 by 1.2 by 0.2, again multiplied by our acceleration due to gravity, which is 9.8. This gives us a total weight of our pad of 6.51 kilonewtons. So then we can now go and calculate for the actual service load, or the actual weight that the pad would have to transmit to the bearing soil. And that would be the 150 kilonewton load that came from, or that the 150 kilonewton load resulting from the dead load that the column will transfer to the pad, the 50 kilonewton load resulting from the live load that the column will transfer to the pad, and the 6.5 kilonewton load resulting out of the weight of the pad's own, resulting for the weight of the pads itself. Now, this gives us a total service load value of 206.51 kilonewtons. Now, going back to check for the amount of pressure that would be exerted on the soil, we pick our actual service load and we divide by the area of our pad foundation. Now, our actual service load has a value of 206.51, and for our pad foundation, multiplying the 1.2 by 1.2 gives us a value of 1.44. So dividing our actual service load by the area of our pad foundation gives us a pressure of, or a bearing pressure of, 143.41 kilonewtons per millimeter squared. From this, we realize that the amount of load that is going to be transferred to the soil in terms of pressure is far below the maximum pressure that our soil can take. Whereas our load being transferred to the soil is equals to 143.41 kilonewtons, our soil can take as much as 200 kilonewtons per meter squared, in which case the load from our pad wouldn't cause our pad foundation to sink into our soil. So then, having come out with our set of dimensions, which would see to it that our pad actually is able to transfer its load onto the soil without sinking into the soil, we'll move ahead and estimate for the load that the pad is supposed to carry. This we have already done, but we want to bring it out clearly so that we'll know how much load our pad has to resist. Now, in estimating for our load, just as we did for our previous element designs, we'll start by calculating for our dead load. For our dead load, we'll look at the self-weight of the pad and every other load that is being transferred onto the pad from the column. For our self-weight for the pad, we had a value of 6.51 kilonewtons, and the load from our column being equals to 150 kilonewtons. This gives us a total dead load of 156.51 kilonewtons. Moving forward, we'll now go and calculate for the imposed loads on our pad foundation. And this is equals to the imposed load coming from the column onto the pad foundation and has a value of 50 kilonewtons. Now, having realized our total dead load and our total imposed load, we can now move ahead and estimate for our design load, which is equals to 1.4 multiplied by our dead load plus 1.6 multiplied to our live loads. This gives us 14 multiplied by 156.51 plus 1.6 multiplied by 50, which yields us 219.11 plus 80 and gives us a total design load of 2991 kilonewtons. Now, the pressure that would be exerted by these 2119 kilonewtons at the base of our part is equals to the load divided by the area, which gives us 299.11 divided by 1.44, with a final value of 207.72 kilonewtons per meter squared. So then that's the ultimate pressure that our part would have to support. Now, having found our ultimate pressure, we'll now have to move on and calculate for the moments that would occur in our section as a result of the pressure being exerted onto the part, or as a result of the pressure that would have to be transferred onto our soil. When it comes to calculating for moment in part, or when it comes to doing a part foundation and calculating for the moment in a part, the moment values are usually calculated along the face of the column. Now, on our screen is the dimensions for our part foundation. Our part has a total dimension of 1,200 by 1,200. Then from the design of our column, as we did in the previous unit, we realized that at our ground floor level, our column had a dimension of 350 by 350. So then superimposing our column on our part foundation gives us the diagram that has been shown on the slide, with the column located at the middle of the part foundation and the dimensions to the size of the column being equals to 425 and 425 in both directions. Now, as I said earlier on, in designing for moment in part foundation, the moment value is calculated along the face of the column. So then we are going to make use of the area from the column face to the end of the part foundation to calculate for our moment in our part, and that area is what has been highlighted or shaded out for us. Therefore, our moment the moment that would occur in our part is giving us the pressure as exerted from our ultimate design load multiplied by the area of the shaded portion, or the area from the face of our column to the edge of our part. Now, once we multiply our pressure by that area, it converts our load into a point load, which will be acting halfway through the distance from the face of our column to the edge of our part. So then, taking moment of that point load about the face of our column, we'll be multiplying that value against half of our distance, which is the 0.425, which would give us a value of 0.123. Hence, having our moment value being equals to the 207.72 multiplied by 1.2 multiplied by 0.425 and 0.123. Now, finding the product of this would give us a value of 22.56 kilonewton meter. Hence, the moment at the face of our column is equals to 22.56 kilonewtons per meter. Now, because we are dealing with a square column, if we take our part foundation in both planes, that is in the x plane and in the y plane, we'll have our moment values being the same. Why? Because we have our part being a square part. Had it been that our part was a rectangular part, then it means that within the two planes, our moment values wouldn't have been the same. So then, having calculated for our moment in the x plane, would have had to go also to our y plane and calculate the moment at the face of the column within the y plane. Now, once that we know the value of our moment at the face of our column, we can now go ahead and check if the initial dimensions we give to our part foundation is adequate to resist the moments that we've encountered. So then we move ahead and do our adequacy of section. Again, also, you'd agree with me that for the part foundation that we are designing for, it is rectangular in shape. And once it's rectangular in shape, it means that we can make use of the rectangular design of what? A section. Now, if we are making use of the rectangular design of a section, then it means that for our adequacy of section, we can say that our K value is equals to what? M divided by FCU BD squared. where our m value is equal to the 22.56 kilonewton meter that we have calculated for. So then our k value is equals to m over fc d squared. Now, from our initial dimensioning, we had a total part depth of 200 millimeters. Now, from our total part depth of 200 millimeters, you're now supposed to come and estimate our effective depth from the other elements that we designed before, that is being the slab, the beam. We realize that our effective depth is equal to our overall depth minus our cover to reinforcement minus half our bar diameter. Now, because for this design we are making use of a cover to reinforcement of 20 mm and a cover to reinforcement of 40 mm and 20 mm mild steel bars, our D effective is going to be equals to 200 minus 40 plus 10, with the 40 plus 10 being in parentheses. This gives us a D effective value of what? 150 mm. Now, having determined our D value, we can now substitute our D value together with the other parameters into our K formula to determine the value of our K. We had our moment value being equals to 22.56 times 10 raised to the power 6 being divided by 35, which is our grade of concrete, multiplied by 1,200, which is the breadth of our part foundation, multiplied by our D effective, or our D squared, which we just calculated as 150 millimeters. Now, finding the product of these values gives us a value of 0.037. So then our K value for our moment is 0.037. We'll now move ahead and compare this K value to our K prime value, which is the K value would get assuming our section is at its maximum moment point. So then comparing our K to our K prime value, we realize that our K value, which is 0.037, is less than our K prime value, which is what? 0.156. Now, having identified that our K is less than our K prime value, it means that we can go ahead and design our section as a singly reinforced section. Meaning that for our part foundation, we can go ahead and design our part foundation as a singly reinforced part foundation. Now, with that one being said, we can now go ahead and do our moment design for reinforcement. From our slab design and from our beam design, we realize that the area of reinforcement for a rectangular sectioned element was given by moment divided by 0.95 FYZ, with our Z value being less than or equal to 0.95 D. For simplicity's sake, we always equated our Z value to the 0.95 of our D, in which case our area of steel reinforcement was equal to our moment divided by 0.95 Y multiplied by 0.95 D. Substituting the various parameters into it gives us our area of steel reinforcement being equal to 22.56 multiplied by 10 to the power 6. Everything divided by 0.95 multiplied by 250 multiplied by 0.95 also multiplied by 150. Now, this yields us a total area required for our part foundation of 666.59 millimeters squared. And just as we've been doing for the other element, we'll now go back and look at the diameter of steel reinforcement we decided to use, find the area of one of such bars, then divide the area of reinforcement required by the area of one of those bars. That would give us the number of bars that would need to make up for the area of steel reinforcement. Once we find that area, which mostly would be in the decimals, we'll convert it to, or we'll round it up to the next whole number. Now, whatever whole number that we get for the number of reinforcement that we need, we distribute it equitably over a meter span. After distributing it equitably over a meter span, whatever we get becomes the center to center spacing of our reinforcement.